Every time you zip a folder, save a PNG, or stream a video, there's a good chance an algorithm from 1977 is quietly doing the heavy lifting. It's called LZ77, a text compression algorithm, and by the end of this video, you'll be able to compress and decompress text by hand. Hey everyone, I'm Ali, and this is Codemaster. Compression means representing the same information using less space. Most real-world data, text, images, code, isn't random. It repeats. The same words, the same patterns, the same runs of characters show up again and again. Compression algorithms exploit that repetition. Instead of storing a repeated pattern every single time it appears, you store it once. And every future occurrence just points back to it. LZ77 does exactly that. To make this happen, every compression system relies on a two-part partnership, the encoder and the decoder. Think of the encoder as the translator. It takes your raw, bulky original text and, following a strict set of rules, converts it into a highly optimized, unified object that takes up far less storage space. The decoder is the mirror image. It takes that compact, rule-bound object and perfectly reverses the process, interpreting the tags to reconstruct and retrieve your exact original text, byte for byte, without losing any information. Let's start small. Imagine part way through a text file you find this 5 A's in a row. That's 5 characters. And since each character in ASCII typically takes up 8 bits, storing this raw costs us 5 times 8, 40 bits. LZ77. Whole idea is, can we say the same thing with fewer bits? Here's the trick. Somewhere earlier in the text, 10 characters back to be exact, this exact pattern of A's already appeared. So instead of writing the A's out again, LZ77 writes a tag with 3 parts. First, position. How many characters to jump backwards to find the start of the match? In our case, that's 10. Second, length. How many characters to copy moving forward from that point? That's 5, since we're copying 5 A's. Third, the next character. The character that comes right after the match, which is B. So the tag is 10, 5, B. That one tag replaces all these 6 original characters. Now let's calculate how big this tag actually is. The position field value is 10, which is represented by 4 bits in the binary numeric system. The length field is stored in 3 bits, and the next character is a normal character, so it costs the standard 8 bits. Added up, 4 plus 3 plus 8 equals 15 bits per tag. Compare that to the 48 bits those 6 raw characters would have cost. That's less than a third of the size, from one tag alone. You might be wondering, why does the tag need that next character field anyway? It actually serves a brilliant purpose. It guarantees the algorithm always makes forward progress. Think about after compressing the previous sequence. What happens to the character Z? And Z has never appeared in the text before. The position and length fields would both be 0, because there's absolutely nothing to copy. Without that next character field, the encoder would have nothing to output. By attaching the raw character, the tag can smoothly represent that brand new Z and keep moving. Here's the simplest possible case. The very first character of a piece of text. There's nothing to match against. So the position value is 0. The length value is 0, since no characters could be copied. And the next character is just the literal character itself. The tag becomes 0, 0, A. This is exactly how LZ77 handles any character it hasn't seen before. So far, we've only looked at one isolated tag. But how does the algorithm actually move through an entire file? It uses a pointer. Think of it like a cursor on your screen, sitting right between the text we've already compressed and the text we still need to compress. Every time the encoder creates a tag, that cursor jumps forward. In our previous example, the tag represented 6 characters, 5 A's and a B. So the cursor simply skips past those 6 characters and prepares to compress whatever comes next. The text sitting directly behind this cursor is called the search buffer, which is the text we've already processed. And the text right after the cursor is the look-ahead buffer, which holds the upcoming characters waiting to be compressed. Let's put everything together and compress a full string, one step at a time, these 22 characters. Watch how the cursor moves, sometimes just one character at a time, and sometimes jumping several characters in a single leap. Step 1. The search buffer is empty. There's nothing behind us yet. No match is possible. So we output the tag with position 0, length 0, next A, the literal character A. The cursor moves forward by 1. Step 2. Now the search buffer holds a single character, A, but the next character we need to encode is B. They don't match. Again, no match. So we output position 0, length 0, next B. The cursor moves forward by 1. Step 3. The encoder sees an A at the start of the look-ahead buffer and scans the search buffer for it. It successfully finds a match 2 positions back. To see if it can get an even longer match, the encoder moves to the next character in the look-ahead buffer, which is another A. But when it checks the search buffer for both characters together, the sequence AA, it doesn't find a match. Since it can't extend the match, it stops right there. The longest match it found was just 1 character long. The character immediately following that match becomes our literal next character, which is A. So it outputs the tag, position 2, length 1, next A, because this single tag successfully represents 2 characters at once. The cursor jumps 2 steps forward. Now keep your eyes on the screen. Watch how the algorithm repeats the same steps we explained again. Searching for B, found a match, 3 steps back. Searching for B, A, found a match. Searching for B, A, B, didn't find a match. The literal next character is B. The cursor jumps 3 spots forward. Now searching for A, found a match, 2 steps back. Searching for the sequence AA, found a match, 5 steps back. Searching for the sequence AAB, found a match. Searching for the sequence AABB, didn't find a match. The literal next character is B. The cursor jumps 4 spots forward. Now we get to see one of the most brilliant tricks in LZ77. The rest of our text is a massive run of 10 Bs in a row, ending with a final A. There is a special feature of LZ77. When a pattern repeats, the encoder is allowed to keep the match going, stretching right across the cursor and directly into the look-ahead buffer itself. To compress this, the encoder tries to find the first B. It finds a B just 1 step back. Then it tries to find the sequence BB. It finds that match 2 steps back. Next, it tries to find a sequence of 3 Bs. But it doesn't find any match in the search buffer. And here comes the trick. When there is no match in the search buffer, the encoder is allowed to look for a match inside the look-ahead buffer, but only among the characters it has already matched, which are the character colored in blue. By looking at the blue characters, the encoder successfully finds a match of 3 Bs, 2 before the cursor, in the search buffer, and 1 right after it. The encoder keeps this rhythm going until it reaches the final character, A. It doesn't find a match for it, so A becomes the next character. So the tag is position 2, length 10, next A. This single tag captures 11 characters all at once. The cursor jumps all the way to position 22, and we've officially reached the end of the string. And that's it. The entire 22 character string compressed into just 6 tags. Let's measure the payoff. In LZ77, the size of each field is strictly fixed. It is determined by the biggest possible number that field will ever need to hold. So, if the highest number we use for the position field is 5, which requires 3 bits, and the highest number for the length field is 10, which requires 4 bits, then every single tag will use exactly 3 bits for position and 4 bits for length, even if the tag is just holding zeros. Add the standard 8 bits for the next character and we get a fixed size of 15 bits per tag. Our 6 tags cost 6 times 15, 90 bits, while our 22 characters cost 22 times 8, 176 bits. That the compressed version is almost 50% smaller than the original. So let's take those exact 6 tags and decompress them, rebuilding the string 1 tag at a time. The rule is simple. For each tag, use position field to jump back into the output we've already rebuilt. Then use the length field to copy forward the given number of characters, then add the next character. Let's watch it happen.